Welcome to this interesting topic, metals. The way this topic is going to be discussed is we're going to start with characteristics of metals. So these characteristics, actually we discussed them in the topic, the periodic table. So it's going to be kind of a revision, and also we're going to build up from what we learned. So after we get done with characteristics of metals, we're going to take a look at the reactivity series, which we also discussed just an intro when we were doing the periodic table. Then when we get done, we're going to take a look at recycling of metals. So this video is going to end on recycling of metals. The next video is going to concentrate on extraction of metals. So this subtopic, extraction of metals, deserves a good treatment. So I will try to deliver it into 2 videos so that all the important points are included. Once we get done with extraction of metals, we're going to finish this topic with a subheading called alloys. Let's get started. So what are some of the general physical properties of metals? We're not going to take a look at chemical properties. I think we exhausted those when we were studying the periodic table. So we're going to concentrate on the physical properties. So the first physical property is metals are good conductors of heat and electricity. The second is metals are malleable, which means they can be hammered into thin sheets. So the one way you can differentiate a rock which is not a metal or some wood which is not a metal is when you try to hammer them, can you hammer them into thin sheets? So to hammer them into thin sheets, you should be able to get something like this. So any metal, you can get something like this. The third property is metals are ductile, which means they can be drawn into long wires. Unlike other non-metallic things, you cannot draw them into thin wires. So metals are capable of being turned into something like this. The next property is metals are sonorous. So to be sonorous is to produce sound when hammered. You get a metal, you hammer it, you're going to get a very good sound. Then we have metals are lustrous. To be lustrous is to be shiny. So when you get a metal, you cut it, you are going to see that the side that has been cut is going to be shiny. Okay, so that's what it means to be lustrous. So another physical characteristic is metals are solids at room temperature and pressure, except for mercury, which is a liquid at room temperature and pressure. So all metals are solids, but there's one which is stubborn and it's not a solid. Remember when we were studying thermometers, we talked of liquid in glass thermometer. So one of the liquids that is used other than alcohol is mercury. It is a metal, so it looks like this. So its symbol is Hg, mass number and proton number there, and this is how it looks. For those who are old enough that they have watched the Terminator series, maybe you remember what used to happen to the Terminators when they are shot and the likes. So this is mercury, the only metal which is a liquid at room temperature. The last property is metals have a high melting and boiling point as compared to other groups of elements. Next, we take a look at the reactivity series. So the other name for this thing called the reactivity series is activity series. What is it? So the reactivity series is just a list of metals with the most reactive metal at the top and the least reactive metal at the bottom. So what they did is they got metals, then they reacted them. They reacted or tried to react them with water, which was cold or warm, steam, and also acids. Then based on the outcome, the metals were arranged with the most reactive at the top of this thing called the activity series. So here is the activity series. By the way, in both types of reactions, whether it's the reaction with water, steam, or acids, so long as the reaction takes place, hydrogen gas is formed. and this point you're going to see its importance. So this is the reactivity series. So in the reactivity series, we have potassium as the most reactive metal. Then we have sodium, calcium, magnesium, aluminium, zinc, iron, lead. Then we have hydrogen. Is hydrogen a metal? No, it behaves as a metal and as a non-metal. It's not a metal. So what is it doing here? So I'll explain what it is doing here soon. Then we have copper, mercury, silver, and gold. So what is expected of you is to know this reactivity series. You have to know which one is more reactive between potassium and sodium, which one is more reactive with sodium and calcium. So I remember I had created a memory aid when I was at school. So it for example, it was posokama, just like that, till I mastered. But these ones which are below hydrogen, I never cared much for a reason that you are going to see soon. But you have to care. You have to know that gold is the least reactive, silver is more reactive than gold, mercury is more reactive than silver, and copper is more reactive than mercury. So according to this reactivity series, when you react these metals with water, which can be cold water or home water, or steam, which is water that has evaporated, or an acid, the metals from potassium to lead are capable of producing hydrogen in that reaction. But metals that are below hydrogen do not react with those three. There was no reaction, meaning that there was no hydrogen that was produced. So hydrogen is used as a center or as a benchmark or as a line that separates or demarcates these ones which are able to produce hydrogen to these ones which are unable to produce hydrogen because they cannot react with water, steam, or the acid. Okay. So now with this knowledge of the reactivity series, we would be interested to know what can we use this knowledge for? Where can we apply this information? But before we do that, we're going to carry out 3 different experiments just to see how these metals react with the 3 things, that is water, which can be cold or home, steam, and an acid. With that being said, we continue. So just one more note: when metals are arranged based on their ability to form positive ions, they form another series called Electrochemical Series. So there's also another kind of another series, another list, which lists metals according to their ability to form positive ions. Remember, a metal is expected to lose an electron and therefore to become positively charged. But some metals do that easily. They lose an electron easily. Others, they find it hard. So there was also another experiment which was tested to see which ones, which was carried out to see which ones are able to lose electrons easily and which ones are not able to lose electrons easily. So a list was formed and it is called the Electrochemical Series. The fun fact is the way metals are appearing on the reactivity series is nearly the same as the way they are appearing on the electrochemical series, meaning that the ones that are reactive on the reactivity series also lose the electron easily. So they are on top of the electrochemical series. So it's supposed to be lost, not lose like this. Yeah, as in losing. So so metals that lose electrons more easily are said to be electropositive or to be more electropositive. Then the ones that find it difficult to lose electrons are said to be less electropositive. Now we can go to our 3 different experiments. So the first involves reacting metals with water. So in this experiment, we get a metal, we react it with water. What's going to be formed is a base, okay, or an alkali, which in short, the symbol of the metal is going to combine with the hydroxide. Then hydrogen is going to be given out. So let's take a look at these reactions and the results. So the first is potassium. When potassium was reacted with water, what happened was the reaction was observed to be very violently with cold water, and it produced potassium hydroxide and hydrogen gas. So the key word is the reaction was very violent, which shows that potassium is very reactive. Then sodium, also the reaction was also violent. Okay, what about calcium? Calcium, the reaction was less violent. If you just observe here, they all produce hydrogen and hydroxide, metal hydroxides. What about magnesium? So for magnesium, it reacted very slowly with cold water, but violently with steam. So why is it that it reacted violently with steam? Remember when we talked about when we were doing rates of reactions, the factors that affect or influence the rate of a reaction, one of them was temperature. So when water is heated, we expect a reaction that is far much better than when it's cold. So these three, potassium, sodium, were able, actually these two, potassium and sodium, were able to react with cold water because they are very reactive. But calcium did not react that fast with cold water. Then magnesium, it was even worse, till it was reacted with steam, where it was violent. The reaction was violent. What about aluminium? So aluminium does not react with cold water. Okay, we expect this since we are going down, the reactivity is reducing. So reacting with cold water should be difficult. Even now, reacting with warm water should also be questionable, but with steam, maybe. So aluminium does not react with cold water, but reacts slowly with steam to form aluminium oxide and hydrogen gas. Okay, so aluminium is a bit different. It doesn't form hydroxide, it forms oxide, and they have seen the changing here. So actually, aluminium is said, if you remember, to form amphoteric oxides on types of oxides. Okay, which means it can form both basic. It can form oxides that have both basic and acidic characteristics. Zinc does not react with cold water, but hot zinc burns in steam. Okay, so it does not react with cold water. Again, it does not react with steam unless you heat this zinc. That's when it will react with steam. So things are getting worse. Iron does not react with cold water, but reacts slowly with steam to form iron oxide and hydrogen gas. Then after this, lead is above hydrogen. Copper, silver, and gold are below hydrogen on the reactivity series. So these four have the same behavior, and the behavior is they are below hydrogen in the reactivity series. Therefore, they do not react with cold water, not even steam. So these ones do not react with cold water or steam. So there is no reaction. Next, we go to the reaction of metals with hydrochloric acid. Reaction of metals with hydrochloric acid. So in this reaction, a metal is going to react with hydrochloric acid, then it's going to form a chloride, okay, metal chloride, and a hydrogen. So that's how this reaction is. So this is the general equation for these kinds of reactions. So with this general equation, let's see how they now behave when we react them with hydrochloric acid. So one key factor we should note is all metals above hydrogen in the reactivity series react with the dilute hydrochloric acid to form a salt and hydrogen gas. The salt is the chloride. With that being said, let's take a look at the reactions. So potassium with the acid, it's explosive as expected. Even sodium, it is the same, and of course these are the equations which we expect. Calcium, it reacts vigorously to give calcium chloride, so expect this because calcium is reactive. Magnesium, it reacts rapidly. Zinc reacts quite slowly, we expect this since we are going down. Iron reacts slowly also. Then lead, slow and only if the acid is concentrated. Remember, lead is above hydrogen, so this one is able to react slow, but only if the acid is concentrated. Then copper, gold, and maybe silver, no reaction even if the acid is concentrated. So why are we talking about the acid being concentrated? Again, rates of reactions depends on the concentration. The higher the concentration, the higher the rate of reaction. So we expect that once the acid is concentrated, we expect the reaction to be fast. Okay, and for lead, that's when we see some reaction, but it's slow. Then copper, gold, silver, nothing. Then there's also a good reaction where metals react with oxygen. Okay, so I talked about water, steam, and acid. Also oxygen, we can see how the metals fare when they react with oxygen. Sodium catches fire. So when you react sodium with oxygen, there's going to be a fire actually. So because of this, sodium should be stored in such a way that it is covered by very unreactive elements such as gold, silver, and lead. Otherwise, sodium, whenever it is exposed to oxygen, catches fire. Magnesium also catches fire. Iron does not catch fire, but the hot metal glows brightly in oxygen and gives off yellow sparks. Copper does not burn, but the hot metal becomes coated with a black substance. So when you heat copper and there's oxygen, it's going to have a black coating around it. Gold and the friends, no reaction no matter how much the metal is heated. With those experiments now being concluded, we go to displacement of metals from their compounds. Remember, when we finished talking about the reactivity series, I posed the question, what or where can we apply this knowledge of the reactivity series? So the application is in displacement of metals from their compounds. So let's say you have this metal, then you want to remove it, and this metal, let's say it is in a salt or it is combined with something. So what you want is the metal. You don't want the other thing that is combined with the metal. So how do you remove that metal? So use the knowledge of reactivity series. How? So the truth is, a metal that is high in the reactivity series will always displace a less reactive metal from solution of its compound. So if a metal is more reactive, you combine it with a compound of a metal that is less reactive, that metal which is less reactive is going to be removed and replaced by the metal that is very reactive. Okay, so if you want to get that metal that is combined with something that you don't want, just get the reactive metal. Then that reactive metal is going to remove it and it will combine with that thing that you don't want. Then you're going to have your metal as a free element. For example, copper sulfate. So iron is more reactive than copper on the reactivity series. So when you combine iron and copper sulfate, iron is going to take the place of copper, such that we're going to have iron sulfate and copper is going to be ejected here as a free element. So here there are some errors here, but anyway, what to get in terms of the chemical formula, but what to get is the place of copper is going to be taken by iron. The other example is this, where copper reacts with silver nitrate. So now silver is less reactive than copper. Copper is more reactive. Copper is going to take the place of silver, such that silver is going to be ejected. The other example is this one. So iron and zinc. So the question is, which one is more reactive between iron and zinc? So if you recall the reactivity series, zinc is more reactive than iron. So iron can't take the place of zinc in this compound. So there will be no reaction here. Displacement reaction won't happen. Finally, we look at recycling of metals. So as we keep on using metals to make maybe phones, like the motherboards for phones, to make cars and the likes, they are finishing up wherever we're getting them. So the idea is, once we use, let's say, a car, maybe it is involved in an accident, it is thrown away. The idea is to get the metallic parts of the car and then reuse them to make something else. So that process is called recycling. So what are some advantages or reasons for recycling metals? First, better conservation of natural resources so that reserves last longer. So reserves is of course where we get these metals. So if we are recycling those ones which we use, it means we won't be going there to get them. Therefore, they will stay and they are going to be used by generations to come. Again, with recycling, less mining will take place. And you know the effect of mining, its pollution and the likes. Mean that if there's less mining taking place, it means there'll be less air pollution and less water pollution. Third is, it's more effective waste disposal as scrap metal is recovered. Okay, so the issues, the problems surrounding waste disposal, the scrap metal, which makes part of the waste, is recovered, and therefore we won't have issues to deal with garbage. But recycling comes at a cost. It is sometimes not possible because of the costs involved. For you to recycle, for example, aluminium, there is an issue of locating where that aluminium is. Then, of course, you have to transport that aluminium from where it was thrown to where it should be reproduced. The reproduction process also involves energy. There's heating and the likes. So, because of that, there's cost. There's money that is involved to recycle. So if that money is not going to proportionate or is not going to be equal or greater, equal or less than the money that's going to be or the profit that's going to be made when the recycled metal is being sold, then recycling cannot occur. So that is one downside of recycling. This marks the end of this topic. Actually, not topic, this part of the topic. Happy solving.